Hello students, in this second part our objective would be to look through the priors. As I said that in my first part discussion that the prior plays a vital role in drawing inference on the parameter of interest, but how to choose the prior, the question comes up, and we will talk about that more or less technically to actually differentiate different kinds of prior, like some may be subjective, some may be objective, and some may be conjugate priors, some may be other priors of interest like reference priors, and this choice of different priors will play a vital role in drawing inference on theta. So we first of all try to explain that what is the distribution, prior distribution, if it is continuous, if it is discrete, and then what is the normative or objective choice of the prior. And if we do not assume anything about the prior behavior, like we say that when the parameter theta is totally unknown to us, then shall we take the uniform prior? Can it give us really no information about theta? So we will see through that, and after that we will consider different situations like under the case of standard distributions like the normal distributions, like the discrete distribution like the Poisson distribution or binomial distribution. We will see that how the choice of priors influence the inference. I mean, inference means what you know is the posterior inference. So how the choice of prior will combine with the likelihood and give us the right inference on the parameter theta of interest given the data set. All right. So that's my objective in this particular session, and if time permits, we will go for the computational techniques and other things. In this part, the whole emphasis is on prior distribution. What is prior selection? How its distribution to be taken? That is of our interest here. Now, we can interpret the prior distribution to be frequency distribution, or it's maybe a normative and objective representation. In particular, in a case where the state of ignorance, in a case where we do not have any idea about the parameter theta. Now, what is prior frequency distribution? Sometimes the parameter value may be generated by a stable physical mechanism that may be known or inferred from previous data. We will explain it later on, okay, through some examples. In many situations, that has a physical interpretation in terms of the frequencies. So the priors are obtained in terms of the frequencies, and you look at the histogram of the prior, it looks like the behavior of the distribution is something like normal or gamma or some other standard distributions of interest. Now, what is normative and objective interpretation? Specifying a prior distribution for a parameter about which nothing is known. Okay? So when nothing is known about the parameter theta, so what kind of prior distribution can we take? And if theta can only have a finite set of value, it seems natural to assume all values equally likely a priori. So when nothing is known, the question comes up, can we assign in the finite interval range of the parameter theta, can we assign equal values in a sense that equal chance of occurrence of every value of theta? So whether the ordinates are same for all values of theta in that finite range, it may be of that interest to us. Now we talk about the continuous parameter first of all, like its invariance arguments. Like for a normal mean mu, argue that all intervals between a to a plus h should have the same prior probability for any given h and all a. This leads to a uniform prior on the entire real line. You might have noted I said that it's a normal mean mu, and I'm going to take the prior for the parameter mu. Okay, and it has the same prior probability for any given h and all a in the interval a to a plus h. So maybe we can then assume that it's a uniform prior on the entire real line. You see that as soon as you take the uniform prior on the entire real line, it happens that the prior doesn't exist, in the sense that if you integrate over the whole range, it comes out to be infinity. So it diverges, it blows off. Okay? And so what to do? We'll discuss it later on. And for a scale parameter sigma, so instead of mu, if we consider the variance sigma, and we may say that all values in the range a to Ka have the same prior probability, leading to a prior proportional to 1 over sigma. And again, this can be seen to be improper in the sense that integrate over the whole range will not lead to the value 1 or any finite value. So there are some problems with the uniform prior. Even if you assign equal probability at each point or each values of the parameter theta. Okay. Now, however, if theta is uniform, the random variable theta, or we call it theta h, is uniform, and arbitrary nonlinear function g theta is not. So what I'm saying, I'm trying to illustrate it through an example. You see that, so if you take pi theta to be 1 uniform or theta positive, all right? So suppose you are interested in, you assign the probability uniform prior for that, right? Pi theta equals to 1 when theta greater than 0. Now, if you are interested in some function of theta, like say gamma equals to log theta, okay? So it is quite natural that if you do not have any idea about theta, you also do not have any idea about the parameter gamma, because it's basically log theta. You do not know theta, so how come you will be able to know that log theta? So again, if you want to assign the uniform prior for theta, which is to pi theta equals to 1, you must assign the uniform prior for gamma, pi gamma to be 1. But it doesn't hold true, because it is a function, gamma is a function of theta, and through Jacobian it can be seen that the new prior for gamma is e to the power gamma. So it varies over different values of gamma. So we are not assigning equal probability for every values of gamma. So it's a counter situation where you have assumed uniform prior for theta, but when the scale changes, you are not having the uniform prior. Okay? Is it possible to use then? Basically, there is a whole set of explanation for that, how to justify that, how, I mean, it can be shown that in the case of location invariant family, where change of location doesn't affect the whole problem, the pi theta equals to 1 is absolutely all right. So if you change from theta to some theta plus a, some location change, it doesn't really affect your new parameter eta, which is theta plus a, to have the, I mean, what you can say that you can take the same prior pi eta to be 1. So there is nothing wrong taking the prior to be uniform, pi theta equals to 1 in the case of location family. But in the case of scale family, it really matters. And that last example was in the case of scale family, where the prior distribution for theta and prior distribution for gamma really varies. Okay? So Jeffrey, with strong explanation, has defined a prior which remains invariant under any change of scale or location. His definition is: take prior pi theta to be information matrix, determinant of I theta to the power half. So I theta is basically the Fisher information. Okay. Let's see that how Jeffrey has computed these for binomial distribution, for some other standard distribution. If you look through that, you see that we need to have the, like in the previous slide, you see that pi theta is essentially minus expectation of x given theta del 2 over del theta to log of fx given theta, this whole thing to the power half, right? And then we compute it for binomial setup, and it comes out that in this case the Jeffreys prior determinant of I theta to the power half, or I theta to the power half in this particular case where theta is a scalar, is really theta to the power minus half, 1 minus theta to the power minus half. So this is basically a beta density with parameter half and half. So Jeffreys prior, the conclusion is that Jeffreys prior for binomial distribution is proportional to beta half half. We can compute the Jeffreys prior for some other distributions too, like for partial, for normal mu and normal sigma. You see that the Jeffreys prior comes out to be pi lambda equals to is proportional to lambda to the power minus half. Pi mu, when sigma is known, is 1. Mu belongs to this. Incidentally, this is the location invariant. So the location invariant prior and Jeffreys prior matches. Match, and then you consider the normal sigma. Pi sigma is 1 over sigma. So this is the scale invariant prior that way. Now what is the problem? The problem is that pi theta, when you take pi theta to be 1, like in the previous setup for the normal distribution, you have taken pi mu to be 1, and this is not a prior density, it's not a density, because if you integrate, it blows off, the whole thing diverges, right? So what we can do is that we can see even if the prior becomes improper, can we use this prior for combining with the likelihood to get ultimately the posterior in a valid way? So my point is that, is it possible that even if the prior is improper, combining it with the likelihood gives you a proper posterior distribution? Because unless it is proper, you are not able to draw inference on thetas based on the posterior distribution. But it seems it can be shown that in many situations, even if the prior distribution is improper, the posterior distribution turns out to be proper. And here we'll see some other situations where the improper prior will lead to improper posterior. So suppose you have y1, y2, yn independently normally distributed with constant variance sigma square, and with expectation of yj, the mean turns out to be some nonlinear function like this, where as usual we assume that rho lies between 0 to 1. So what we can do is that we can assume some uniform prior for rho, and gamma, beta, and sigma have some improper priors. Like you know that sigma, for sigma we can take proportional to 1 over sigma. For beta we can take, even for gamma we can take proportional to 1. Gamma is 1 because it is a location parameter. Beta is scale parameter, so it should be proportional to some scale constant, or proportional to some 1 over beta or something like that. So then for any observation y, what I mean the observation, a particular any set of observations I am talking about, so y is a vector, the marginal posterior density of a rho is proportional to this thing, where you know that h is a bounded function and has no zeros in 0, 1. This posterior still has an improper distribution on 0, 1. So what is the conclusion? Conclusion is that even if you start with some improper posterior prior distribution, combining with the likelihood in some situations will give you proper posterior so that you are able to draw inference properly. But in some situations like this example, where improper prior will lead to improper posterior, so inference will be totally wrong in that case. The situation where improper prior gives you proper posterior is demonstrated here. You see that suppose given theta, x1, x2, xn are IID normal theta 1. Here theta can take any value from minus infinity to infinity belonging to this parametric space theta h. Now I take for inference on theta, I take pi theta to be uniform prior. Pi theta is proportional to 1. Like the previous situation in the case of normal distribution, I said pi mu is 1. Here we take pi theta to be 1, and with that we compute the posterior distribution, and that is very proper distribution. You see that it is implied from there, that it is very clear that from there the theta given the data follows normal with mean x bar and variance 1 over n. So what is happening here? Even if you take some improper prior, pi theta is proportional to 1, so that integration over pi theta d theta will give you infinity. It's a divergent. So in that case, you still get the posterior distribution to be a proper distribution. Okay. Another example, say you have Poisson distribution, all right, and you take pi theta to be 1 over root theta. So again, theta lies between 0 to infinity. This is the parametric space, and if you integrate over pi theta d theta, it is infinity. So it's not proper. The pi theta is improper distribution. Despite that, you would see that the pi theta given data comes out to be a standard gamma distribution. It's a very proper distribution. So nothing wrong in taking the proper prior, improper prior, so long as you get the posterior to be proper. So what I'm saying, I repeat, nothing wrong taking improper prior if the result giving you the posterior distribution comes out to be proper. So all posterior inferences could be drawn by using such a proper posterior distribution, like in that case you have gamma distribution. Now we can come to that subjective degree of belief. You see, last time I talked about the objective and normative. We'll talk about the other choices of prior, like conjugate priors or reference prior if time permits later on. But we talk about the subjective degree of belief. You see, what I'm saying, that subjective degrees of belief, that means I feel the prior should be like that, so I take the prior accordingly. It's not that I am influenced by someone. This is my gut feeling that theta should take certain value with certain probability. So that the subjectivity comes out for a particular person at a particular time. There are many ways of eliciting subjective priors, like in some binomial experiment, beta prior is taken for the parameter of interest, to where beta, alpha beta are taken to be same. In that case, say A and B are taken to be same. What does it mean? It means the chance is 50-50. You see that because when you take the beta prior, the mean for this prior distribution is half. Because you say that it is A equals to B, that means the mean comes out to be A over A plus B. So the chance is half. So it's a sort of rational, impartial prior, though it is subjective. But there are limitations of this kind of subjective prior because it varies from individual to individual. Now there are also some other problems. What if the prior and the likelihood disagree substantially? The result is that the posterior will be totally different. I mean, posterior will be contradicting in the sense that it neither favors prior nor favors likelihood. The subjective prior cannot be wrong, but may be based on a misconception. I'm not saying that the person who believes in certain subjective prior, certain prior for theta is really wrong, but it is based on some misconception he has got or she has got throughout some experiment, through some experiment or elsewhere. It may be the model may be substantially wrong. Okay, the model that has been taken for considering the likelihood function, that has been taken to be substantially wrong. Often use hierarchical models in practice. We'll talk about that later on. The general comments is that comments are that determination of subjective priors is difficult to assess the usefulness of a subjective posterior because it is completely one's own individual thinking. So what a person will be thinking about the prior is very difficult to say, and it's very difficult to assess its usefulness. And don't be misled by the term subjective. All data analysis involve appreciable personal elements. Now, Bayesian compromise between data and prior. The posterior variance, if you compute this, is on an average smaller than the prior variance because what is happening is very clear. What is happening is that likelihood is giving you some more input, some more information, so that you are combining. So whatever the prior variance someone is taking, it is being reduced by the use of the data information. So that's why the posterior variance is usually on an average smaller than the prior variance. And reduction is the variance of posterior means over the distribution of possible data. The posterior summaries usually one draw after computing the posterior distribution is they go for posterior mean, posterior median, posterior mode. These are all the location, posterior location parameters of interest. And also one can go for the credible interval or highest posterior density interval for different posterior distributions. Let us just give you some basic idea about the conjugate priors. I'm going to explain the conjugate priors later, but in the case of different families of distribution, the conjugate priors comes out correspondingly as this. So binomial n theta, the conjugate prior is theta, prior for theta, right, is beta alpha lambda. For Poisson theta, the prior comes out to be gamma delta naught gamma naught. For normal mu sigma square, where sigma square known, the conjugate prior is mu normal mu naught sigma naught square, and so on. So this is how the conjugate priors have to be chosen. But what is conjugate prior? The conjugate prior is the prior such that the posterior distribution obtained by combining the conjugate prior with the likelihood gives you some distribution which belongs to the same family of distribution of the conjugate prior. So what I am saying in a nutshell is that conjugate prior and posterior belong to the same family of distribution. All right. So like I just give you one scenario, like when you take the binomial n theta, when you take the prior for theta to be beta, when you combine this likelihood and the prior, the posterior distribution belongs to the beta distribution. I said that prior and posterior belong to the same family of distribution. Now, how to choose this conjugate prior? The technique is that it is basically through the likelihood. One can develop the conjugate prior which is mimic to the likelihood function. So mimic to the likelihood function will lead to ultimately the conjugate prior. And the advantage is that when you develop, looking at the likelihood, develop the prior mathematically or technically, it's in the most of the circumstances, it is easier to cope with, it is easier to deal with or getting the posterior distribution because the likelihood and conjugate prior, they can analytically give you a better result or simpler result. Okay, so this is the advantage of conjugate prior, and this is how the conjugate prior has to be constructed. And one can go for posterior predictive density of a future observations, like the new observation or future observations given the data is unlike the Fisherian or the classical procedure. Here we use the posterior density of theta. So when you multiply the new observation likelihood with the posterior distribution of theta given the data set, then integrate over theta to ultimately give you the predictive density of the new observation given the data. Like in the binomial setup with such and such values, n equals to 20, x equals to 12, number of successes, a equals to 1, b equals to 1, you see that probability, what is a and b? Is the prior parameters, like when the prior parameter theta follows beta distribution with a equals to 1, b equals to 1, then you can compute by using the posterior predictive density formula. You can compute the probability y tilde equal to 1 given data that will come out like this. So what is happening that when you have the prior density for theta, when you have the data set, you combine these two to get the posterior density, and you also look at the new observation. The new observation density is combined with the posterior density to get ultimately posterior predictive density. That's how it has been obtained. So students, what we have learned in this second part? We learned how to choose a prior. What is a prior? First of all, what is normative or objective prior, and what is some prior with some frequency distribution. So prior with some frequency distribution is a setup where you have some behavior on the prior distribution, and we have the frequency so that we can go for the histogram and other aspects from the prior distribution. Sometimes from the previous study we can have some idea about that. But normative or objective prior means when we do not have any idea about the prior behavior or prior parameter, so then we assume that it is uniform over the line. Like if it is a finite interval, no problem. For every value of theta, you assign equal chance. So it is the same ordinate. But when it is a real line, if you assume uniform prior, that creates some problem also. Because if it is an uniform prior in the real line or flat prior in the real line, then it may be improper, because integrating over the whole real line gives you the value of the prior density to be 1. So integration over the prior density will lead to the value, it will lead to the value infinity. Okay. So this is a divergence prior, and it's not improper. So what we do is that we look for some other prior can be chosen or not. Now what is happening, another disadvantage of this uniform prior is that it is not scale invariant. If you change the scale, the prior doesn't remain constant over the interval. So uniform prior is not really suitable always. Jeffrey later on suggested some non-informative prior, and then he computed that for different distributions, how we can compute the non-informative prior. And also then we talked about the conjugate prior, and what is conjugate prior, what is the advantage and other things. And also for that conjugate prior, we can show that different posterior distribution can be easily computed. And finally, we showed that how to compute the predictive density for a new observations to be introduced. So for a new observation to be introduced in the Bayesian setup, you go for finding the predictive density given the data. That means using the posterior density against a normative prior or any conjugate prior or any other prior of interest. You combine this predictive or the new observation density function with the likelihood, or with the posterior to ultimately get the predictive posterior density, and you can draw your inference accordingly.